Now we're going to see if we can generalize some properties of limits at infinity for polynomials and simple rational functions, just to make the process of evaluating limits at infinity for more complicated polynomials a little bit easier here. So here we have n be a positive integer and p is a polynomial. P of x looks like this. This is just the general form of a polynomial, and for right now you don't need to worry about that. We're not going to talk about that until the very last property here. So it says the following are true here. So first one, part A right here, says limit as x approaches positive or negative infinity of x to the nth is always positive infinity when n is even. And these we can, I think, show pretty easily here. So if I have limit as x approaches positive infinity of x to the nth power, now I'm going to take infinity and sort of quote-unquote plug it in and do a little bit of math here. I would caution you on doing this too much. Here we can do it because really what we're going to be interested in at the end of this is the signs. But remember that infinity is not a real number. It does not follow all of the same rules. But as far as multiplying and dividing by negative numbers, it will play by that rule. That's fine. So here if I take infinity and again, quote, plug that in, I'm going to have infinity times infinity, times infinity here. But all of these, remember, are positive. So this is a positive times a positive times a positive times a positive. So I have all of these positive numbers. When I multiply them together, I'm going to get, well, another positive number. And even here, if you don't want to do too much like mental arithmetic here with infinity, just think about this as a very large number times a very large number, a very large number, a very large number. I'm going to end up with another very large number, a very large positive number. So here we'll end up with positive infinity here. So I think that one's pretty easy to see. The other case, if x is approaching negative infinity here, x to the nth, this one's perhaps a little bit trickier. But here I'm going to take negative infinity times negative infinity, and we'll do that a certain number of times here. Negative infinity times negative infinity here. So here we want to be careful, because now we need to worry about these negative signs that we're going to be dealing with. But the key part of this here is that, n is even here. That's what we want to keep in mind here, is that n is even. So when it comes to dealing with this, I know I can kind of divide each of these by 2. I can sort of pair up these negative infinities, and I can say, well, negative times a negative, when I take those two together, that's going to give me a positive. Here at the end, a negative times a negative, I know that's going to give me a positive. And then I kind of actually collapses back into that same argument that we just made before. We say, okay, now we just have a bunch of positive numbers once we pair those off. And once we take a bunch of positive numbers and multiply them together, we'll get, well, positive infinity here once again. And if we understand this property here, the next one I think should follow pretty similarly here. So now we have a limit as x approaches positive infinity of x to the nth is positive infinity. This time, though, if x approaches negative infinity, then x to the nth will approach negative infinity when n is odd. So let me do this in a different color here. So here in this case, if limit as x approaches positive infinity of x to the nth, just like we did in the last one here, we've got positive infinity times positive infinity, right, a certain number of times here times positive infinity, where all of these numbers are positive. It's going to look exactly like the argument that we made in part A. We've got a bunch of positive numbers together here, so we're going to end up with another positive number. They're all infinity, right? So infinity times infinity times infinity times infinity, however many times, is still going to be infinity. The new case, though, the one that's perhaps a little bit different here, says, all right, now this time, if x approaches negative infinity of x to the nth, this time we're going to approach negative infinity. And again, it all relies on this part right here. It says when n is odd here. So here I'm going to have negative infinity times negative infinity, a certain number of times here times negative infinity here. And again, I can do kind of the same thing I did in the last example where I'm going to pair off most of these. So I take a negative times a negative, that's going to give me a positive, right? And I'll take a bunch of these in the middle here, pair them off. But then at the end here, I'm going to have one extra negative number here because n is odd. They're not going to pair off exactly nicely. It's odd. It's not divisible by 2 here. So I end up with one negative number here at the end. So I know first of all, I'm multiplying a bunch of infinities here. So I know I'm going to end up with infinity. And then if I look at the signs up here, if I look at these signs up here, I've got really a bunch of positive numbers here. I've got a bunch of positive numbers I'm going to multiply together here times this one single negative. Essentially, I've got a positive number times a negative number, which gives me that negative number here. So hopefully those are relatively easy to follow, not too bad. C, this one is really interesting, and this is one of the more powerful ones we'll be using here. This one says, limit as x approaches plus minus infinity of 1 over x to the nth or x to the minus n. This guy sorry about that. This guy right here and this guy right here actually say the same exact thing. That's just a different way to write those. And actually that'll be tremendously important to us in the next chapter. Being able to switch back and forth using negative exponents is going to be something that is going to be very, very helpful to us. So we're going to spend a lot of time talking about that in the next section, in the next chapter, excuse me. But in either case, if x approaches positive or negative infinity right here, well, it's going to approach 0. So this one I think is a little bit more interesting. I'm going to use this notation right here just because I think we're a little bit more familiar with it. That's the one I prefer to use. So we'll change our color one more time here. So this time I have limits as x approaches positive or negative infinity, 1 over x to the nth power here. If we want to, we can go ahead and just apply that property here, that limit property that says, you know what, I can take the limit of the numerator and the limit of the denominator. So limit as x approaches plus minus infinity of 1, limit as x approaches plus minus infinity of x to the nth. Now if I look in my numerator here, if I'm just looking at this limit of 1, that's just a constant. It's just going to stay at 1. Here, in my denominator here in this case, limit as x approaches plus minus infinity of x to the nth here, well, if I look back at the last two, we said your result is either going to be positive infinity or negative infinity. It's got to be one of those two. So it's either plus or minus infinity. And for this problem, I don't really care which one. It doesn't really matter. Plus minus infinity here. So essentially I end up with this thing that looks like plus minus infinity. And this is a really tricky thing to deal with if you're just looking at this. 1 divided by infinity, I don't really know what that means. And I've cautioned you before. I've said try not to do too much mental math with infinity because it doesn't play nicely here. But what we can do is I'm going to off to the side over here. If I think about just say 1 over x, right? If I think about different values for 1 over x, and actually here, let me give myself a little bit more room. Let's do this right here. If I look at, say, different values of 1 over x, what happens if our denominator gets bigger and bigger and bigger, but our numerator stays exactly the same? So if, let's just take x equals to 10 first of all. If you looked at 1 over x, if you looked at 1/10, and actually we don't even need x equals 10. If we were to look at 1/10, right, perhaps we're not great at visualizing fractions. We're better, I think, at visualizing decimals. This is 0.1. 1 divided by 100, this is going to be 0.01. 1 divided by 1,000, this is 0.001. 1, and so on, right? Hopefully we're starting to see the pattern here. 1 divided by 10,000, 0.0001 here. So if you look, we have a similar behavior here where the numerator is staying exactly the same. It's always 1. But look at the denominator. The denominator in this case, the denominator for each one of these is increasing. It's getting closer and closer to positive infinity right here. And then, okay, just look at the y values here in this case. Well, What are the y values approaching? 0.1, 0.01, 0.001. These numbers are getting smaller and smaller until we approach 0 here. So if you have a finite number in the numerator and either positive or negative infinity in the denominator, I know that that is going to approach 0. And really, we kind of talked about positive infinity right here. If you wanted to stick a negative sign in front of these, the only thing that's going to change here is, so if I take a negative sign right here, I have negative 0.1. Now I'll have negative 0.01, negative 0.001, and so on. So I still get closer and closer to 0 just from the opposite side, just from kind of the negative direction, if you will. So that one's pretty nice. So I'm going to use all three of these then to prove this last one, and I think this is a really kind of neat proof to see. So this one says if you look at the limit of, remember that this guy right here, p of x, that's just an arbitrary polynomial here. Then you can look at the limit as x approaches plus minus infinity of a sub n x to the n. And this guy right here, this is just what is known as your leading term, which is hopefully a term that you've heard before. Your leading term, it's the power of x, or the term of your polynomial with the highest power or the highest degree here. So you can basically just look at that first term in the polynomial, first term if it's in standard form, right? You're going to look at that leading term and basically ignore everything else, and you just look at that one single leading term. And it simplifies the process of looking at limits at infinity for polynomials a whole lot. So I'm actually going to prove this one because I think it's kind of a neat little proof here. So let's see. Let's start with limit as x approaches plus minus infinity of p of x. So here I'm actually going to write this out. Limit as x approaches plus minus infinity. If you look at how p of x is defined, it's a sub n x to the nth power. So here I might have, say, x to the fourth. And a sub n right here, this is just saying some coefficient right here. Plus another number times a slightly lower power of x, right? So here I might have x to the third. And you continue that process forever and ever until until at some point you'll end with a power of x squared, a power of x, and then perhaps a constant term there at the end. So what I'm going to do, and you wouldn't normally do this, I am going to factor out x to the nth power from every single one of these terms. And it's going to look a little bit silly, but just try and follow along with me. I'll do my best to explain myself once I do this. So I'm going to factor out that x to the nth power here. So limit as x approaches plus minus infinity. Here I'm going to have x to the nth power. So here I'm factoring this out. Let me do that in red so it's a little bit easier to see. X to the nth. And then, okay, so what will I have here? So if I factored out from that first term, I'm just left with, well, a sub n. I factored out the x to the nth. That part's gone. Plus this second term's a little bit tricky here. It might be difficult to see. I'm factoring out x to the nth, but here I only have n minus 1 powers of x. It's kind of like if you had, say, let's just take an example down here, x to the fourth plus x cubed, and you wanted to factor out x to the fourth. So here I'd be left with 1 plus, well, there's actually only 3 powers of x here, so what are you left with? You're actually just left with 1 power of x in your denominator this time. And if you don't believe me, let's check your work. X to the fourth times 1 would give us x to the fourth. X to the fourth times 1 over x, we'd cancel the power of x, giving us x cubed. So we end up with a power of x in the denominator. And I won't get too lost in how many powers of x right here, but you'll end up with something that looks like a sub n minus 1 divided by x to the first here. And that's going to happen for all of these terms, because all of these terms from here on after, all of these terms have a lesser power of x in that leading term, because that's how the leading term is defined. So all of these are going to have some power of x in the denominator these last few terms here, I'll have a squared over x to the n minus 2 plus a sub 1 all over x to the n minus 1 plus a naught all over x to the nth. So this is what it would look like here. And then what I'm going to do is I'm going to apply my limit laws here. I'm going to look at the limit as x approaches plus minus infinity here of x to the nth power times the limit of everything else here, that other, the piece that I factored x to the nth from. So here I've got just the a sub n plus a sub n minus 1 all over x plus blah, 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 blah. I'm not even going to write the rest of these here. Well, I probably should here, because the next step's really cool. N minus 2 plus a sub 1 all over x to the n minus 1 plus a naught all over x to the nth. Okay, so this is very, very cool. So this first piece right here, this piece right here, I don't really know what it goes to, because it's going to depend on the power of x, whether n is even or odd. But to be honest, for this part, I don't really care. I'm going to say limit as x approaches plus minus infinity x to the nth. So now I'm basically going to be taking this limit statement and I'm going to apply it to each one of these terms. Now really I should write out that process for every single one of these terms, but it's going to be a little bit tedious here, and we'll hopefully be able to identify a pattern very, very quickly here. So I'm going to look at limit as x approaches plus minus infinity. So I'm going to look at this first term here, a sub n. Well, that's just a constant, so it doesn't have any impact. Oops. Actually, here I should drop my limit statement. My apologies here. Let's actually just drop that limit statement, because we're actually going to evaluate this limit right here. So if I take the limit of a sub n, we said that's a constant, that's just a sub n. But here, for this next term, here I've got a constant, a sub n minus 1. So remember, this is just a constant here, divided by a power of x. Well, if x is approaching plus minus infinity, what does that go to? Oh, if only we had a property that maybe we had proved a few moments earlier that showed us. Well, it turns out we actually do right here. This says if you have a constant, or 1 in this case, divided by any positive power of x, that's going to approach 0. And you could apply a couple limit laws here to show that it works for any constant, not just 1, but it's the case here that this guy right here, this next term, this is going to go to 0, plus da-da-da-da-da. All of these guys have powers of x in the denominator, which means they're going to go to 0. Every single one of these terms goes to 0, which I think is really, really cool. And then at the end, so okay, we can kind of collapse these two and we can say, all right, well, what am I left with? Limit as x approaches plus minus infinity of just x to the nth times a sub n, or a sub n x to the nth, which is exactly what I wanted to show way up here. That's exactly what I've got down here. So my proof is done. So these properties are going to help us tremendously in the next video when we start to look at some more complicated examples of limits at infinity of polynomial functions.